me start the recording. So, I guess everything is okay now. I guess I'm audible. So, let's begin with our session 6. Right? So, this is our session 6. Now, in this part, we mostly will discuss about what? Thermodynamics itself, because thermodynamics is a vast one. So, it takes time to understand, right? So, we will discuss mostly about thermodynamics. And yeah, sir has given some home assignment, right? In what session, like first lecture, right? This week. So, I will try to derive it, but not totally. All you have to do is just assume some situations and you will get the answer. So I will give you the what do you call the empirical correlation. So yeah, I will derive the empirical correlation. From there you have to define the cases, like case 1, what is greater, what is less, and case 2, what should be approximated. So yeah, if you do that, then that should be helpful. So now, moving on to what we have discussed last session. So the first one is the delta G mix, right? So initially I had A, and then I had B, right? Now we are trying to mix it. So you get AB. Yeah, that is what we get. So these are AB. Now we know the initial. What is our initial G values? Let's say A has NA number of moles, B has NB number of moles, and molar free energy of A is G naught A, and molar free energy of B is G naught. Then G initial, the total energy for our system is G naught A plus G naught A. G naught A. So we have G naught A and G. Now, this is G final. Okay. Now in G final, what's happening? So G final should be, let's take GF. Then it should be GI plus delta G mix. Or you can write the change in energy when you mix two things is given by G final minus G initial. Right? So if you want to find the final free energy, which is GI plus delta G mix. Now what is our GI? GI is NA G naught A plus NB G naught B. Right? And we have derived delta G mix many times. So for let's only take for like random solutions. Right? So perfectly random solution and also a perfectly random ideal solution. So if we take for ideal solution, then and also for random, then it should be delta G mix will be XA ln XA. So only we are considering a binary alloy, because we are only considering two elements, right? So it's just a binary alloy. So XA ln XA plus XB ln XB. So these are final correlation. For what? For random ideal solutions, right? So you can write it as ideal solutions or random. Because the atomic positions are completely random, right? The probability is like constant for any atom to the next position. So that's why we call it as a random solutions. Perfectly random solution. So anything is not perfectly random because we are only considering it for only the mathematical correlation, that's all. So this for G final, right? And then, so what else we need to discuss today? So we know what is G final. I hope everyone knows the derivation of this part because I guess sir and me, myself has also derived this part. So I will not derive it again. Right, so if you have any doubts, you can ask me. So, moving on to, from here we arrive to what? The chemical potential, right? Now, chemical potential tells us that what? The concentration gradients, if you are talking about in terms of concentration, there is a concentration gradient, and for in terms of diffusion, again there is a concentration gradient, and in metallurgy you will see there is an uphill diffusion and downhill diffusion. So far we know like this, right? So if you have higher concentration C2 and you have lower concentration C1, then the atoms will diffuse from C2 to C1, right? This is what we have seen. So everywhere in nature we see this, but in metallurgy you will sometimes find this guy also. You have C1, which is a lower concentration, which is C2, which is higher concentration. And the atoms will move from here to here. Right. Actually, you see in diffusion or normally, right, in normal potential energy diagrams or what else. So, if you have a slope here, right, and you just throw a ball, you don't even have to throw the ball, right? All you have to just leave the ball. It will come down. Why? Because it has higher potential energy. Right. So here I have higher potential energy. Yeah, there's this one. I don't know what's. So if this is my plane, now what I'm trying to do is I'm just leaving the ball here. Will it stay there? No. It will just come down. Why? Because it has potential energy. Right. So that's what happens. And same goes if you have higher concentration C2 and if you have lower concentration C1. Right. For example, if you just spray a bottle of perfume here. Right. I'm standing here and I have sprayed here. So what happens is, because the concentration is very large here, but over here the concentration is zero away from it. So that's why the perfume or whatever the air or the gas will flow from here to here to the surroundings. Why? Because the concentration gradient. So once the concentration is same throughout the medium, then it stops moving. Right. So this is what we see normally. But in metallurgy, both this will also happen and this will also happen. Right, the concentration is moving against the concentration gradient, right? So this is a lower concentration, this is a higher concentration. Still the atoms are moving from lower to higher. So this will become even small and this will become large. Right, so this is called as what? This is uphill. See, we are climbing here. So that's why we call it as uphill diffusion. This normal one, where I have C2, I have C1, flow of atoms, it is called downhill diffusion. So how is this guy possible? Right? This guy shouldn't be possible. So ball shouldn't move from here to here. Right? It seems not possible. Then that's why here we invented a term called chemical potential. Now how does it look like? It looks like this. Mu. So what does it measure? That's the question. So it measures the activity of the components. And activity is given by A small a. Right. So if you want to find the atoms, whether they will move up or down, then you should know the activity. Activity of a component. Whether it is A or B. Right. So in this term we have considered A or B, right? A and B. So that's why it is a component of is an activity of component A or B. Now, so far so good. We have designed our term for chemical potential. Then we have designed for our component called activity. Now what does activity mean? Activity is nothing but it tells you about the trueness of the solution or the true concentration. Solution or true concentration. That's all. So if you want to find the chemical potential, then you need to find the activity of the solution. If you can find the activity of the solution, then that's it. The chemical potential can be easily measured. Right, now, so far we have seen terms chemical potential, activity. So activity tells about the true concentration of the solution, right? Whether it is a higher concentration or lower concentration. Now, how do I relate the activity to the chemical potential? Right, because we have seen free energy or so delta G mix. If I take, okay, so delta G mix will be equals to XA ln CA plus XB ln XB, or G final will be equals to XA G naught A plus XB G naught. Oh my bad, I didn't mention here, it should be N by 2 because everything is mode fraction. Okay. It will also be mode fraction. Now, plus XA ln XA XB ln. Now what I am trying to do is I am trying to differentiate with respect to XB or XA. Okay. So this will turn out to be G naught A. This will be minus G naught B. Why? Because XB can be written as 1 by 1 minus XA. So dou by dou XA will be, first we will differentiate 1, it will become 0, then it will be minus 1. So that's why minus 1. Plus so differentiation by parts, then first I will differentiate XA, then I will remain with ln XA, and if I differentiate ln XA, then it will be 1 by XA into XA will be 1. So I will write 1. Now same goes here. XB, you differentiate, you can write as 1 minus XA, then it will be minus 1 ln XB plus now I want to differentiate ln XB. So if I differentiate ln XB, it will be 1 minus XB. Then again I will differentiate the XB, this will be minus 1. So it will be minus 1 XB into XB. So sorry, XB into 1 by XB, it will be again 1. So I hope I am clear because this is a simple step. So all you have to do is do differentiation by parts. So I will just do it for this guy. So XB can be written as 1 minus XA ln 1 minus XA. So if I differentiate, let me do it in another slide. XB ln XB can be differentiated as d by dxa. We know 1 plus XA plus XB equals to 1. So now 1 minus XA ln 1 minus XA. So let's differentiate 1 minus XA first. Then ln 1 minus XA will come out. dy dxa of 1 minus xa plus, so 1 minus xa will remain calm this time, so we will differentiate dy dxa of ln 1 minus xa. So ln 1 minus xa at first remain calm, then we will differentiate first 1, we will have 0, then I differentiate dou xa by dou xa, it will be 1, okay, plus coming to this guy 1 minus xa is calm, so first differentiate ln, then it will be 1 by 1 minus xa, then again you will differentiate the inside term, right? So this guy will get cancelled, so again this will become minus 1, so finally we have minus of ln 1 minus xa, that is, I can directly write it as xb, right? I don't need to write again 1 minus xa, I will write it as xb minus 1. So that's why we have g naught a minus g naught b ln xa, this plus 1 minus 1 will get cancelled, and then I have minus ln xb. So I will group these terms, okay? G naught a ln xa, oh sorry, I'm using a g naught a, group, not literal grouping, okay? G naught a minus ln xa, this will be one term, right? And plus g naught b plus g naught b minus right. Now let's remember this guy as 1. So now, and we have defined what is chemical potential of a component is given by chemical potential of a is given by rho g upon rho m. The change in free energy of a, or you can write it as this. Change in free energy when you add something, or when you add Na moles, what is chemical potential? What is the chemical potential of B? Rho G by rho NB. So this is G total, or G final. I can write it like this: dg total chemical potential of A, dg total chemical potential of B, dnB. Right. Now, if you want to write it, the total change, the total change should be dg. Right, so dg will be given as mu a dna plus mu b dnb. If I am writing for total number of moles per mole, then dg is lesser than dg dash. Now dg is equals to, because it is now per mole, so mu a dxa plus mu b remember this. So you cannot do this like so we have why not we can add. So we have one equation and then another equation. You add 1 plus 2, then it will be 2 times out. We get rho g dash. You can write it like this. MA, DMA. And this term is equals to this guy. So total change and the DG, the change in free energy. Okay? Now, and that's why I wrote it like this. The total change. The total change in free energy will be the chemical potential times dxa plus b plus chemical potential times the dx. Right, now that's how you arrive to this equation. Because we have defined our chemical potential. Right? What is the chemical potential? Chemical potential is nothing but the change in free energy when you add any moles. And the chemical potential B is nothing but the change in free energy when you add any moles. Right? Now, why? We can even write like this, So, Na plus Mb equals to T, Nt, right? So, Nt. If I differentiate, then no. If I do the like divided by Nt, then it will be Xa plus Xb equals to 1. Then it will be dxa equals to minus Vx. That's how it is. Now, if you compare these guys, if you compare equation 1 to equation 2, what do you see? Now, for example, if I differentiate this again, so I have dg equals to mu a dxa plus mu b dx. Now, if I differentiate with what? dxa, okay, then mu a will be remain minus mu b. So no, I will not tell you because I have also derived. So dxa will be equals to minus vx. Just like I have said here. Now let's say this is equation 3. Now if I compare this one with 3, what does it say? It tells me that chemical potential of A will be equals to G not A P ln Xa mu B G not B RT ln XB. So if I want to write G, it will be equals to mu A Xa plus G final will be equals to mu B. Okay, so this is our main relation, which tells me that how the final energy will change with respect to chemical potentials. Okay, and there is this another term, sir has forgot to told, there is this Gibbs-Duhem equation. What is this Gibbs-Duhem equation? It is very important equations in thermodynamics because it makes sure that we can solve the activity equations. If you want to solve like how do I say? So if you want to find the chemical potential of components, if you want to do the calculations and find the chemical potential of any elements, then you need this Gibbs-Duhem equations. So how how these are useful. So how do we get some information from this? Let's go to that point. Okay. So before that, before going into the Bostonian equation, I hope the chemical potential point is clear. So GA will be mu A x ray, PV x v, and G is for. And again, for regular solutions or for standard solutions, okay. So for standard solutions, we introduce the term enthalpy because the delta G mix is equals to delta H mix minus T delta S mix. So delta H mix is equals to delta U mix the change in bond energy or the release in energy, either it is due to bond breaking or bond forming, plus P delta V. A constant pressure. Okay, we are only considered. Everything in metallurgy we do at constant pressure. I mean the most parts. Like for example, if you do annealing or anything like normalizing, quenching. So anything you take, we do it at constant pressure. Right? We are not changing pressure. So that's why the pressure is taken as 1 atmosphere. Okay, so this is it. Then, and we also consider, for example, A is molar volume is E not A, and B has molar volume of V not A. Then the final volume will be AB. It should be V not A plus V not B. Okay. Then what is the change? X is equals to V naught A plus V naught B minus V naught A minus V naught B. If it is just like this, then these two will get cancelled. Delta V mix will be 0. Okay. Now, for some reasons, if V naught A plus V naught B is greater than V naught A plus V naught B. V naught A is final, this is initial. Then you have delta V mix greater than 0. So, if two types of elements are combining to form an alloy, if there is a change in volume, then delta V mix can't be 0. Okay? So if you are solving for that, then we need to consider this also. But for now, let's say the volume is not changing on mixing. The final volume. Okay. So then this term goes to 0. Then what is my internal energy term? So delta H mix will be only equals to delta H mix. U mix will be equals to delta H mix. And what is delta U mix? Delta U mix is related to bonds formation and breaking. So again, I have derived this part in my previous session. I am not going to do that again. So delta U mix will be equals to coordination number, how many bonds are lost, times Avogadro number times probability of finding A, XA, and the probability of finding XB, aside of it will be XB, times omega. Now what is the omega? Omega tells me what is my bond energy that's been released, or the total number of bonds that has been formed. bonds are formed because we are mixing A and B, right? So A bonds are being broken, BB bonds are also being broken, and new type of bonds are forming, that is AB type of bonds. So I want to know number of AB bonds have been formed. Then, so all this, if you substitute here, then everything will turn out to be Z, N, A, C, B, you will get what? Energy, right? So if I take out these terms, the constant terms, then I have, if I put these three terms, 1, 2, 3, because these are constant, they will not change. Avogadro number is a constant, will not change. Coordination number is a constant, will not change. The bond energies are constant, they will not change. So if I put everything into one term, and that is called as omega times HCA and this is my delta H mix. Oh, so now if I substitute this delta H mix into like how do I say? So far so good. We found out what is delta H mix. And if I substitute this delta H mix in delta G mix equals to XA, XB, omega plus there is XA, right? XA mix. So this is my delta S mix, P delta S mix, and this is delta H mix. Right. Right now, so what I'm trying to do now is, so again let's write it in terms of chemical potential, because that's the thing we want to know. Right? We want to find out what is our chemical potential. So moving on to that, we want to differentiate everything in terms of mu A, XA plus mu B, or XA mu A plus XB. Let's write it like that because everyone has seen. How do you write this term in two forms? How do you like divide XA and XB? So the simple term is, we know omega XA. So starting with this, what I'm trying to do is I'm multiplying this guy with 1. Again it will be same because 2 times 1 is 2. Nothing will change. Okay. Then what is my 1? 1 can be written as XA plus XB. Let's multiply them. But still you see 2 terms here, XA and XB there. So let's write everything in terms of XB. Then it will be now we can write this. Okay, so omega let's write first 1 minus xb square xb 1 minus xb square xb again compare 3 to 4 UA will be equals to and the same goes for UB. Now this is for my chemical potential of A. Okay, this is for chemical potential of A. Now if I involve the enthalpy term, right? Now, so these all about chemical potential. I hope everyone is clear now with what do we do with chemical potential. Right. Now coming back to Gibbs Duhem equation, which I was explaining before. So let me write this guy. Gibbs Duhem equation. So I know my G final will be equals to what? Or I can write it like this. G will be equals to BDE minus SCE plus UA DNA DL. Okay, so we know the pressure is constant, that's why dP will be 0. Now if we are doing that like constant temperature, like we are mix out, for example we are mixing water and sugar. Water is component 1, sugar is component 2. We are mixing at constant temperature, right, room temperature. We are not raising the temperature or anything. That's why this is also 0. Then Dg at constant pressure and temperature, I equals to 1 to n mu I dni. So this is about the change in free energy when we add some moles of some component. If we are talking about A and B, then it is about adding A component into A solution, into AV solution. Right? Now, what I am trying to do now is, friends, so then D, sorry, let's write G equals to mu A NA plus mu B. Okay. Now, if I differentiate this guy, then what happens? Let's differentiate first mu A, first NA, okay? So mu A dNA plus mu B dN. Now if we try to differentiate mu A, then d mu A NA plus NB d mu B. So Eg will be equals to mu A dNA plus mu B dNB plus NA d mu A plus NB d mu B. Now we know dg is equals to this guy is equals to this guy, right? So they both cancel out. Now what is the term remaining here? It extra term that is remaining is sigma I equals to 1 to n ni d mu I equals to 0. Right, in simpler form, because that's what we got. dn1 d mu1 plus n2 d mu equals to 0. Let's just change 1 to a, 2 to b. Okay, numbers will be very easy to. Right, so that's why I wrote it as like this. Now you might ask, sir, what do we get from this guy? See, at first that's why I was doing all these equations to make sure you understand why I am deriving all these equations for the chemical, in terms of chemical potential. See, you have the chemical potential here. Now what I am trying to do is, I will write the chemical potential term here. Okay? So chemical potential of A is equals to, at first I have 1 minus XA whole square plus RT log XA. Now what I'm trying to do is I'm trying to differentiate with respect to A. Okay? Then this guy will not change, so constant will not change. The only change that is going to happen is with dxa. Okay? If I divide it by total number of moles, then this can be written as xi d mu I equals to 0. So this will be this guy, and 1 minus xa. So d by dx of a power n will be equals to a power n minus 1 d by dx of a, n into a power n minus 1. I hope I am not wrong. So please correct me if I am wrong. This is my 2. So n into x power n minus 1. Yeah. Then I again have to differentiate a, so it will be minus 1 plus RT by XA dxa. So I have RT by XA minus 2 mu 1 minus XA. So far so good. Okay? Now what I'm trying to do is, I'm trying to put this guy here. So then this will turn out to be, let's take two elements for simplicity. Then let's take 1 and 2. We are mixing A and B. Right? So A is represented as 1, B is represented as 2. Then let's remove the summation because it's 2 terms, okay? So not again, come on back. Yeah. So first I have xi. Okay. Now let's say I'm going to actually write this. Xi d mu d1 plus x2 d mu 1 equals to 0. Right? Now d mu 1 will be equals to minus x2 by x1 into d mu 2. Okay? This is one guy. So d mu 1 is equals to minus x2 by x1. What is my d mu 2? At the 2, all I have to do is substitute a. Okay? So RT upon xd minus 2 mu 1 minus of xd, and then differentiate with respect to xd. So again, now what I'm trying to do is I'm trying to integrate. x2, x2. So multiply this, right? So it will become minus RT by x1 minus 2 mu x2 x2 will get cancelled, x1 will get cancelled, so this will be plus. I have d. So we know dx1 equals to minus dx2. Let's write it in terms of like that. So there are no brackets because we have multiplied with minus, right? So I have to put brackets. So yeah. Now I am reminded with 2 mu dx2. There is minus sign. Minus RT. Let's take RT outside. There is no need to write. So let's do it. Let's write it again. So just pick things out. So I have 2 mu dx2, or I can write it as okay. So dx2 equals to minus dx1, right? So if I do the minus multiplication, then this will again become plus, right? So this minus will become plus. So it will be RT upon x1 dx1 minus 2 mu dx1. This is this guy. Now, chemical potential of pure element is nothing but molar free energy, right? So that can be written as mu1 naught. That is equals to G naught. Ga naught. It's simple. No chemical potential of naught. Right. So you want to know how much is changed. Mu1 minus G naught A will be equals to. So what is this? This would be ln x1. Okay. And then I have minus. Okay. So 2 mu x1, right? So, okay. I hope I didn't do any mistake here. Oh, my bad. So there is also this x1, right? This is x1 will get cancelled. 1 minus x2 here, it will become x1. This guy will cancel. I will have x2 here. Okay. That's the thing. See, just one mistake and everything will get jumbled up. So yeah, you need to be precise when you are writing something. So let me erase this part. 2 mu. So x2 should be 1 minus x1. And I have dx2. Yeah, then it will become plus because I am doing integration. Right? So this will be 2 omega 1 minus x1 whole square times x1. No, not x1. Sorry. See, this equation is very similar. Totally similar to, let's write it as 4. Totally similar to this guy. See? I didn't add here the initial energy, okay? So that is why these equations are useful, the Gibbs dual. This is very powerful equation to solve the chemical potentials, to how to find the chemical potential of thumbs. Okay. So for example, if my chemical potential is changing with respect to some like equation, this is simple one. This is for like regular ideal solutions. And in environment you will not find regular solutions, right? Regular solutions are very hard to find. So you will find some ordered solutions, some non-equilibrium solutions. Then the activity will change, or the chemical potential is not that much straightforward, right? So what again the usefulness? See, you can see all you need to find is one chemical potential. That's all. Then you can find the chemical potential of another. That's why the Gibbs equations are very useful. Right. Now, again we came back to that, right? Because we found out the chemical potential of 2. We wrote it how the chemical potential of 2 is changing. That's all. And from there we found out how the chemical potential of 1 is also changing. Right. So that is the usefulness of Gibbs equation. So for example, what happens if we have 3 elements? You need to find 2, then you will get the another one. Just like the mole fraction. If you know the mole fraction of one element, you can find out the second element. That is very straightforward, but not this guy. So Gibbs equation will make sure that you are able to find out that the other last term that you need to find. Okay. Now that's all about Gibbs equation, and also about the chemical potentials. So I hope I am clear about the chemical potential. So yeah, the other thing we need to know is so chemical potential is equals to what? So far we have found out G naught A plus 1 minus x whole square plus. So what if I can write this term as one term? Okay. What if I can write this whole term as one term in orthogonal? So let's try. So let's write RT ln. Let's represent the term as activity. So that's how we are seeing. Now slowly moving towards activity. Activity of A will be equals to mu 1 minus xa whole square plus RT ln xa. Let's divide both sides by RT. Will be square xa. So then activity of A will be equals to exponential 1 minus xa whole square plus exponential ln xa will be xa. Now, if my solution is an ideal solution, then this guy will be 0. This delta U mix is 0. So then my activity will be equals to mole fraction. And this is Raoult's law. What is Raoult's law? Raoult's law will be equals to gosh, I forgot Raoult's law. What is exactly Raoult's law spelling? R-A-O-U-L-T-S. Pardon me for my spelling, maybe I'm wrong. So Raoult's law is, what does Raoult's law say? So the partial pressure of a component, suppose this is my solution, this is the gas above it, everything is in a container, right? So let's say again 2 components. So partial pressure on a solution, partial pressure of any component on the solution will be equals to, is proportional to the mole fraction of A in that solution. That's what the Raoult's formula is. And to remove proportionality constant, we put total pressure. Right? Maybe that's the Dalton's law of partial pressure. Yeah, the pure partial pressure. Right? That's it. So to remove proportionality constant, we introduce a term called the pure partial pressure of A. Okay, so this is my Raoult's law. Now, how do you equate this, guys? I will write those things again. So PA will be equals to P naught A XA. And the other guy is activity of A equals to XA. Now if I want to equate these two guys, PA upon P naught. Activity of A equals to X. Now this is 1, this is 2. If you equate 1 and 2, then activity of A will be equals to PA pure pressure of, this is activity. Now for ideal solutions, activity equals to mole fraction. What about if I have a non-ideal solution like this guy? If this guy is present, then what should I do? Exponential omega by r. I can write this whole term as activity coefficient. Activity of A will be equals to activity coefficient times mole fraction. Now, what is my where is that guy? Now, how do you equate this guy? Okay. Now, how do I equate this guy to this guy? Let me write that down. Activity of A is equals to exponential RT log 1 minus XA whole square. So if I take XA as a common, then, or I can write it like this, right? I can even write this term as like this also. I don't need to write it in terms of exponentials. So for example, so this will be equals to exponential omega by RT log 1 minus XA square plus 1 times XA. So activity coefficient can be written as, so if I just exponential put this term here, then it will be exponential omega by RT upon XA plus 1 minus XA whole square upon XA. That's it. Or you can even write it like this also. And if I take this as a very small term, then I have 1 minus omega by RT. Either way, it is not a small term, so it's small. So this is my activity coefficient of A. By comparing those terms. Okay, so yeah, activity will be equals to right. So if I take exponential, if I divide everything with exponential, then this will be turned out to be like this. That's all. Now, this is all about activities and activity coefficients. If you have ideal solution, then activity of A will be equals to just a mole fraction. Then if you have non-ideal solutions, then you need to have the activity coefficient times the mole fraction, because it is simpler way of writing everything in one term. And now we know the activity coefficient may be a function of composition. We have two cases. Maybe it is a function of composition, temperature, or just a function of just a composition, or it is just a constant. You have three cases. Maybe it is a function of composition and temperature, or maybe it's just a function of composition, or just it is a constant. Just like people have seen in Henry's law. Now this is my Henry's law. Constant. It will not change. Mostly it will not change. In only the dilute solutions. And it is applicable for only solutes. We are talking about in terms of dilute solutions. That is the Henry's law. So that's how, that is why I first introduced chemical potential, then I came to activity, then I came to activity coefficient. Okay? Same, if you want to find the activity coefficient of A, all you need to do is find activity coefficient of B, and then you automatically will get activity coefficient of A. So all you need to do is find one term. From Gibbs theorem equation, you will find any other terms. Okay? Now, I hope I am clear with these chemical potentials and activities and activity coefficients. Now, check, yeah. Okay, so yeah, so the last part, which is how the composition is changing. The home assignment. Let's do the home assignment part, okay? How the composition affects the, so how my composition affects or my nanoparticle size, right? So this part. How the nanoparticle size will affect the composition. This is what we want to know. How our nanoparticle size will affect the composition. So there were three equations which sir has told. So Let's derive those parts. Okay. So starting with yeah, we know the final free energy is equals to the bulk free energy plus the surface free energy. Bulk energy plus the surface energy. Right. Now what is the bulk energy? Now how do I define my bulk energy? That's the part. Okay, so far we have seen everything we were doing for bulk. We didn't consider the surface at all. Everything we have been doing was for only bulk. So we just substitute the bulk there. Okay. Now if I substitute the bulk term here, so it will be mu A xa plus mu B xa. And we were considering if R equals to infinite. Right? R very large. You are only considering bulk. And what about the surface? In surface energy also you had mu A. No, in surface energy I have 2 gamma volume, okay, constant upon R, the radius or the size of the particle. Okay. Now what is my G final? Or I can write it like this. Right? So if I write everything in terms of MA, because that will be much easier. Now G final will be equals to mu. Okay, so dG final upon d. This will be mu A minus mu B. R equals to infinite, R equals to infinite plus 2 this times. Or you can just write everything like this. Gamma A. So it will be dA by dN. Okay. Now again dG final by dNA will be chemical potential of A, R equals to R. R equals to R minus chemical potential of B at R equals to R. If I put this term here, it will be mu A, R equals to infinite equals to gamma. I can write dA by dN as dA upon dR times R. Okay. Now, what is my dA? dA is 4 pi R square. So it is 8 pi R. Now, what is my volume? 4 by 3 pi R cube times equals to divided by NA is equals to molar volume. Volume of an atom. Right. Now, if I just differentiate, then it will be 4 pi R square dr upon dm. Right. So, what do I need? dr by dna, right? So then dr by dna will be equals to times vm upon 4 pi r2 cancel 2 gamma vm by r. Now coming to here, these guys will be equals to NA, or not N, there will be no N here, right? Because we are already in substitution direction. That's our cost, right? This mu A at so mu A at R equals to R. Okay. So then G naught of A at R equals to R minus, what is plus? It is plus. Oh my bad, it is plus. RT ln XA at R equals to R. And then I have minus G naught of A at R equals to R, RT ln X B R minus G naught of A at R equals to infinite, RT ln C at R equals to infinite minus G naught of B of B plus RT ln XB. Now what the terms are equals? See, G naught A will not change. The molar free energy is constant, whatever you do. Okay, pure, if you are talking about pure. The molar free energy of pure components is constant, whether you take small r or very large r. It doesn't change very much. So I can write G naught A R equals to R and G naught A R equals to R, sorry, G naught B R equals to. So I can take out these two guys, right? What I am reminding you, RT ln XA R equals to R upon XB or XA at R equals to infinite minus RT ln XB R equals to R upon infinite. This is what we have. And then we have this 2 gamma V M by R. Okay, now we assume the cases. What are those cases? If my concentration is very dilute, so XA is less than 1 and XB is almost equals to 1. Okay, then to write this part, okay? XA R equals to R, C R equals to infinite, XA R equals to R equals to infinite, which is equals to case dilute. We have very dilute solutions. Okay, dilute solutions. Case 1. Now what happens? If I'm talking about dilute solutions and case 1, then RT, yeah. So these guys will be remaining there. Right. They will not change. But what about these guys? They will change. See, 1, it will be 0. It will become 1. So everything will be 0. Okay? Because this guy will become 1. This guy will be almost 1. Okay. Now, there will not be very much difference for dilute solution. Either it is xb r equals to r or xb r equals to infinite. If xb is approximately equals to 1 for this guy, then he will be also very approximately equals to 1. He's not very far away. Okay, he will also has a value very approximately equals to 1. So there is no need to worry about that. So we can easily take out this guy. Then what we are reminded with is xa r equals to r, xa r equals to infinite, b equals to exponential 2 gamma vm upon rt. See, I shift rt here, rt will come here, and then I just do the exponential. Log will go there, it will become exponential. Then xa r equals to r, xa r equals to, just let me clean this. Now I can just write it like this also. If this term is very small, so I can even do this term. Okay, I can do this for now. So for example, the whole exponential term, if I remove, for our simplicity, if I remove the whole exponential term, and we know we can from Taylor expansion we can even derive that. So I hope there is no need for me to derive exponential expansion, right? That will be solely on mathematics. So I'm not indulged to do that, but I will write it here. So if you expand exponential, it will be x power 0 factorial by 0 factorial plus x power 1 factorial, x power 1 factorial, just x, then 1 factorial plus x square upon 2 factorial, x cube upon 3 factorial, and then so on. Right, now if my x is very small, so let's say if my x is small, right, if my x is small, then x square will be very small, x cube will be even more small, that's why we just don't involve these terms. And we know x power 0 is 1, 0 factorial is 1, so this will become 1. So exponential of x can be approximated to 1 plus x. So if we do that here, xa power r equals to r, xa when r equals to infinite, 1 plus 2 gamma volume by r RT. Okay, so if my nanoparticle radius increases, okay, so yeah, if r increases, let's put this guy, this is constant, right? This is not change. So let's put this guy as b. Okay, if my r increases, then what happens to b? B will decrease, then my xa r equals to r, now b will decrease, right? So it will not change, it will very much not change. Okay, so because it is going to 0, if b tends to 0, right, that's what happening. If my r is very large, then this b tends to 0, then all I have is, let's write it, right? You know what, let's write this for two cases. Okay, if r equals to infinite, that means my particle is very large, it is in micrometers or meters, not meters, sorry, meters, it is in mm. Okay, and my r is very large, right? So that's why I will put almost infinite. It's not almost infinite, but it is very large. It's a large number. Let's assume it's a very large number, which is that's why we are writing it. Then 1 by r equals to 0, right? And if r is very large, let's say if my r is very large, just like we have particles, water particles, mm to like centimeters, 0.5 mm, 1 mm particle, then my r is very large. My 1 by r tends to 0. It will not be 0, but it is tending to 0. That means we can easily neglect b as equals to 1. So that's why xa and r equals to that's it. Now what happens if my r is small? What happens if my r is small? If my r is small, then this guy r is small, then xa at r equals to r is not equals to sorry, xa r equals to infinite. Right. That is what it is. That is about the first equation where we have derived. Okay. Now moving on to, this is for the single phase, right? We are only writing it for a single phase. What happens if we have two phases? right? So everything we have been writing so far for a single phase. So it is for single phase. Right. What happens if we have a dual phase? Then the chemical potentials will change. Right? So I not only have chemical, so my final free energy will be bulk plus the surface. Now my bulk has two parts. Where's that? Yeah, here it is. So you can see mu A Na plus mu naught Nb, right? So if I write the same term here, mu A Na is what? Chemical potential of A in alpha. Number of moles of A in alpha. Chemical potential of B in alpha times number of moles of B in alpha. This is at R equals to infinite plus chemical potential of B, chemical potential of A times A in beta plus chemical potential of B in B beta, again R equals to infinite, right? The same chemical potential of A, so I will just yeah, why not just I'll write it. Chemical potential of A alpha Na alpha, chemical potential of B alpha Nb alpha at R equals to R minus, so plus chemical potential of B Na beta, potential of B Nb beta at R equals to R. Now you can see the difference, and there isn't this extra term that has been came. So again these will give me what? This term. So RT XA R equals to R, XA R equals to infinite. And what is this? This is mole fraction of A in alpha. This is the mole fraction of A in alpha. So, and then you have RT, mole fraction of B in alpha, mole fraction of B. Okay, this is A. This is in beta. Let me erase this one and write that part again. Okay. This is X mole fraction of A in beta, mole fraction of A in beta at R equals to R equals to infinite. Right, and then same goes for minus the for B also. So okay, let's write. And why that just so oh I forgot to write ln. So let me write here something. Why don't we just multiply? So I have this beta term. Okay. So let's write it for so RT is common. Ln A, ln B, ln A into ln A plus ln B will be ln AB, right? So just write it. Let's write it for that. So let's again. The case is dilute solutions. Okay. So if I'm talking about the dilute solutions, again this guy will go away. Oh no, this guy will not go away. Why? Let me tell you why it will not go away. Let's just write the equation again here. So RT log x mole fraction of B in alpha, mole fraction of B in alpha at R equals to R equals to infinite minus RT mole fraction of what do you call this? Mole fraction of yeah, beta B in beta, mole fraction of B in beta equals to R. Okay. Now let's take dilute solutions. Dilute solutions are nothing but okay. What do you want to consider here? So that is the important thing. The cases that we are trying to consider. So for example, if we are considering a dual phase and where alpha is very lean and beta of, let's say, this is my phase diagram, and I am considering like this. This is my phase diagram, okay? This is my alpha phase, this is my beta phase. So let's say my beta is very lean. That means beta will not take much of A. Okay. So for example, anywhere I can go. This is my solution. Then let's say alpha is also very lean, beta is also very lean. See, the alpha composition here is x B in alpha, right? Here it's B in beta. So for let's write it for alpha. For alpha, XA at R equals to infinite and XA at R equals to R here approximately equals to 1. For beta, XB at R equals to infinite and XB at R equals to R is approximately equals to 1 because both are lean. So what are we remaining? So this guy will go away and XB in beta, XB in alpha. This guy, and the two terms we are remained with is these two guys. That talks about RT log, what do I have? XA in beta, R equals to R, XA in beta, R equals to times XB in alpha, R equals to infinite, XB alpha. You can write it like this, and this is guy is again equals to 2 gamma, but 2 gamma, what is the other term? 2 gamma by R, and I have molar volume. Okay, so simple, that's all. So this is for dual phase. All you have to do is put another phase and then just solve for everything. You will arrive to this guy. Right? It's just simple term. And then you just do some like mathematical jugglery. You just shift RT here and then you put exponential and then you whatever you want to like just want to know. Okay, so This is for this guy and that is for that guy. That's all. It's simple. You do not have to like think too much into this. Okay? Okay. So yeah. R equals to R and R equals to A. You can just put that thing there and then you do the part. Okay? And then yeah, that's all. So let's move on to it is not writing. So that's about solutions. Okay? Now so I hope I have covered everything, right? So, yeah, there is this question in your assignments. So will the free energy depends upon the composition of and the curvature of the grain boundary. Right, so that was the question, right? So let's see whether it will depend on that. Now we know you can write G final as G bulk plus the surface energy. So you can write G bulk as mu A bulk Na plus mu A bulk B plus mu A surface Na surface mu A surface Na surface plus 2 gamma Vm upon R. If you are talking about sphere, then K will be 1. If you are not talking about sphere, if you are talking about some other conical 3-dimensional surface, then that is different. Okay? So now this is my surface sphere, surface energy. See what are the things that defines it? One, my composition, because Na is there. So what are the terms that define here? Bulk. Okay? This is surface. So now the G surface energy, it depends upon this guy. So what are the things that it depends upon? I have number of atoms. That means it depends upon the concentration. And also I have Mb. Again, that is the concentration. And then I have R. That tells me the curvature. That means how the grain boundary is shaped. Right. If I am talking about curvature, then I am also talking about the shape. Right? So that's how. It depends upon the shape, so the composition and the curvature. And your curvature defines my shape. Right? So yeah, so the grain boundary energy will depend upon the composition of atoms there and also the curvature. So that's your option. See, because why I explained this question was, it was very confusing when you don't understand the equation correctly. Okay. If you want to like understand more, then you need to write the equation for the grain boundary. Just like I have did the surface energy for the grain boundary. Okay. So that is about this question, and I hope all the other questions are easy to answer, because if you have like just listen to this session, you could you will be able to easily answer those questions, because I have explained everything in theory itself. Okay, so don't need to worry. You can just email me, because in that Google sheet you got my email or contact address. So if you have any doubts, you can just post there, or you can just email me and ask. Okay, so I will be easily available, so it's not a big issue. So I will try to answer as soon as possible. Uh, yeah, so that's all about today's session. See, the first two sessions were only on, Sir had explained basically the same thing, right? So he, all the two sections, he only explained how the size reflects on your composition, how the size of the nanoparticle reflects on your composition, and he also given 3 equations for home assignment. I have derived this equation. All you have to do is just put the cases. So what happens if you have dilution, what happens if you have another phase, what happens if you have 2 phases with dilute solutions. So yeah, I hope I am clear about it. So that's all for today's session. If you have any doubts, you can ask now, or you can leave the session. Okay, so thank you for attending the session.